Assalamu alaikum. This is lecture number 1 of week number 6. So today we are continuing the fluid dynamics, and we end up with the application of Bernoulli equation. So today also let's see what are the topics we are going to cover today. We will perform some numericals based on the Bernoulli equation and flow measurement devices that we will see. That is also one of the great application of Bernoulli equation. So let us start. The first numerical we are going to do today. The air is drawn into a wind tunnel used for testing automobiles as shown in figure. So this is the figure given. Determine the manometer height h when the velocity in the test section is 60 miles per hour. Note that there is 1 inch column of oil on the water in the manometer. Determine the difference between the stagnation pressure on the front of the automobile and the pressure in the test section. So two things we have to find out. One, we have to find out the height of the column h, and second, to determine the difference between the stagnation pressure and the pressure in the test section. So first of all, we should understand what is basically a wind tunnel. So wind tunnel is basically an experimental setup where we can observe the effect of air pressure and temperature on the different test equipments. So for the test here we have an automobile, okay, and how do we maintain the pressure? There is an exhaust fan and there is an inlet which is open to the atmosphere. So whatever the pressure you need, based on that you increase the RPM of the fan and increase the suction, increase the velocity of the suction air which impart on the automobile. Okay, so based on that, if you want to maintain the pressure, you can increase or decrease the RPM of the fan. If you want to increase the temperature of the air, so you can put some heater or something in the wind tunnel to maintain the temperature. So there is a different setup based on the requirement, what test you want to do. So here we want to see the impact of air pressure on the automobile. So this is one, and here you can see this is the manometer. So this is basically this is not the differential manometer, this is only the manometer, which is we are using to measure the static pressure at point 2. So first of all, to calculate the objective, we give points to the different section. So this is our inlet point and we are assigning point 1. This is our test section. This is, we are assigning point 2, and we are assigning exactly over the manometer section at point 2, because this is the point P2. This is going to be equivalent to the pressure in the height of the column in the manometer, and the point 3 is basically the stagnation point where the pressure we have to determine. Okay, so these 3 points we determine. So first of all, what we have to find out, we have to find out this height h. To find out this height h, we should know this pressure P2. Okay, to find out the pressure P2, we should apply a Bernoulli equation between point 1 and point 2. So to apply the Bernoulli equation, we should know the boundary condition at point 1 and boundary condition at point 2. So this is the atmospheric condition. In the atmospheric condition, we know that the gauge pressure is 0. Okay, in the atmosphere the gauge pressure is 0, because the gauge pressure is measured from the reference of atmospheric line. Okay, and also because this is a open atmosphere, so the velocity is 0. Okay, because open to the atmosphere we do not have any specific velocity, so there is no big change can be observed. So the velocity is 0 in the atmosphere. Normally we do in the case of a free jet also, as you remember. So this is the point 1, the boundary condition, all is known. At point 2, what we know, we have to find out the pressure at point P2. The velocity is known in the wind tunnel, that is 60 miles per hour. So let's see. So we apply the Bernoulli equation at point 1 and point 2. So this is the Bernoulli equation. So the point 1 and point 2 are at the same line, because this is the horizontal pipe, and the horizontal pipe, this Z1 and Z2 are equal, and P1 and V1 is 0 because this is atmospheric condition. Thus V2 in the wind tunnel is 60 miles per hour, and then we convert it into FPS system, because the values of the data is given in the FPS system. So we converted this velocity into FPS system. You can also convert into this inch into centimeter or meter, and you can convert this miles per hour into meter per second, and you can solve this problem with the SI system also. Okay, so here we are continuing with the FPS system. So you put these values in the equation, and finally we end up with this equation. So P2 will be equal to, this is the final equation of rho 2. So we have to find out now the velocity. If you know the velocity, you can find out the P2. So we know the velocity already, we have calculated. So finally we end up with minus 9.2 pound. So you can see there is a negative pressure, there is a suction pressure, because this fan is sucking air from here. So that's why we are getting the negative pressure here. Okay, so this is the indication, the negative static pressure. Okay, so now we have to find out H. To find out H, we have to calculate the we have to make equation for the manometer, because this H is the manometric height. So let's make the equation of manometric equation. How we can make it? So first of all, we have to find out the reference level. So which one is the lowest reference level? So this is the lowest reference level, the pressure at this point. And if you take the line straight from here, and the pressure at this point is same, because the fluid is same and fluid is continuous. So pressure at this point, just starting from H, and pressure at this point is same. So let's make an equation. So up to here, so the pressure at this point is P2 plus, okay, because this is the air, so there is no rho gh we will consider, so only we will consider this part. Okay, if so here plus, because we are going down, so gamma into H, gamma of water into H, and then the pressure here is same as pressure here. Then again you are going up, then it is negative, but this is not water, this is oil. So gamma of oil into gamma of oil. So gamma of oil is not known, it is specific gravity is known. So gamma of oil will be equal to gamma or specific gravity of oil into gamma of water. So that will give you the specific weight of the oil multiplied by height of the column. The height of the column is inches, but it has the FPS system, we measure the height in the form of feet. So we convert this inch into feet, 1/12. So this is the value we have inserted here. You see P2 plus gamma H2H plus gamma of oil minus gamma of oil is going up equals to 0. So from here gamma of oil we calculated, insert the value, and P2 is known. So from here we can easily calculate H, which is 0.23 feet. Next we have to determine the difference between the pressure at 3 and at point 2. So this is the stagnation point. So the point it's indicated here, determine the difference between the stagnation pressure on the front of the automobile. So this is the front of the automobile, and this is the stagnation pressure at 0.3. Okay, and the pressure in the test section and the pressure in the test section, the P2. So we have to find out the difference between P3 and P2. P3 is the stagnation pressure and P2 is the static pressure. So let's see. So now we are going to apply the Bernoulli equation at point 2 and point 3. We write down the equation. Okay, now we apply the boundary condition. The pressure is known at this point, but the velocity is unknown, and the velocity is known at that point. Velocity is 0 and the pressure is unknown. So here what will happen after putting the values? P2 over gamma, V2 square root 2g, and P3 over rho. So we have to find out the difference between P3 and P2. So I took the equation P2 here. So P3 minus P2 will be equal to half rho V square 2. Okay, so the velocity is known, that we calculated already here, and we insert that. Finally P3 minus P2 is equal to 9.22 pound per feet square. Okay, so this is the solution of this problem. Now next move on to the next problem. So far you see in the previous problems we have solved with the constant diameter pipe. The area is constant, but in this problem the area is varying. Okay, if the area is varying, then how we can solve the problem? Okay, if the area is constant, we have done already 2 or 3 problems. Now with a varying area, let's see how we can solve the problem. Excuse me. So air flows through a pipe at a rate of 200 liter per second. The pipe consists of a 2 section of diameter 20 centimeter and 10 centimeter with a smooth reducing section that connects them. Okay, so this is the reducing section, okay, which connecting the larger area to the smaller area. Okay, the pressure difference between the 2 pipe section is measured by a water manometer, and the difference of pressure between the 2 section can be measured by using the U-tube manometer. Okay, so neglecting friction effects, determine the differential height of water between the 2 pipe section. Take the air density to be 1.20 kilogram per meter cube. So here the flowing fluid is air, okay, and no frictional effects. That means the total energy at point 1 is equal to total energy at point 2. So we can apply the boundary. This is the ideal fluid condition, so we can apply the boundary. So what we have to find out? We have to find out the height h. Okay, the pressure difference between the 2 pipes. What is the pressure here and what is the pressure here? So what is the difference? That is height h, that we have to find out. So first of all, what we will do, we will assign the point 1 and point 2. Okay, this is point 1 and point 2. Here the pipe is straight, so the distance from the datum line, the point 1, let's say, so you can see this is the point 1 and this is point 2, both are at the same level, so z1 and z2 will be equal. Okay, so here let's say this is the Bernoulli equation for the point 1 and point 2. Okay, so z1 and z2 is same, so this equation will be reduced to p1 minus P2 equals to rho of air V2 minus V1 square over 2. So we have write down the pressure difference because this h is equals to the pressure difference between these 2 points, okay, into rho gh. Rho gh is equals to P1 minus P2 will give you the height of the column. Okay, so if we know the P1 minus P2, we can easily calculate h. So here we transform the value, we transform the equation in the form of P1 minus P2. So now we have to find out V1 square and V1 and V2. If you know the V1 and V2, we can easily calculate P1 and P2, and if you know the P1 and P2, you can easily calculate the h, because P1 minus P2 is equals to rho gh. Okay, so let's see how we can calculate the V1 and V2. For the V1 and V2, the area is given, okay, and the flow rate is given. The volume flow rate, what is the volume flow rate at this section? The same volume flow rate is that section. If you know the flow rate, if you know the area, you can easily calculate V1 and V2. So let's see here what we have done. We calculated the V1, okay, and V2. Okay, we calculated the V1 and V2. If you calculate the V1 and V2 here, you can easily calculate the value of P1 minus P2. Okay, so P1 minus P2, you calculate the P1 minus P2. Okay, so here now you are going to make a relationship between the h and P1 minus P2. So this P1 minus P2 is equals to rho gh. This is the height. This is the only difference between these 2 points. Okay, so the whole factor P1 minus P2 will be equal to, if you compare this and this together, so this equation will be equal to this. So now V1 and V2 you have already calculated from here. Okay, so if you insert V1 and V2 in this equation, you can easily calculate the value. But here you can see also this height of the column is, here is the density of air and here is the density of water. So this is the density of air, this is the density of water. Okay, so you inserted all the velocity that you have found in that equation and you calculated the height h. Okay, this is the equation, and finally you calculate the 3.7 is the height. Okay, so therefore the differential height of the water column will be 3.7 centimeter. So let's move on to the other problem. In this problem you can see there is a slight difference between that problem. This is also related to the varying area. The area is converging. Okay, the flow is flowing from the higher diameter, higher cross section area to the lower cross section area. But to find out the pressure, we are using a different manometers. To measure the pressure here we are using a piezometer, and to measure the pressure here we are using the pitot tube. Okay, so let's see what is the objective of this problem. So water flows through the pipe connection shown in figure for the given 0.2 meter difference in the manometer level. So the difference of the manometer level is given. Okay, so determine the flow rate as a function of diameter of the small pipe D. So the flowing fluid is water. Okay, and to find out the flow rate we know the equation of the flow rate, Q is equals to VA. Okay, if you know the velocity of this section you can calculate the flow rate. So if you know the flow rate of this area you can easily calculate the velocity and area of the other section. Okay, if you know the flow rate. So to find out the flow rate we need basically the velocity. So what is basically unknown to find out the velocity, and how we can find out the velocity? By using the pressure. How? Because by using the we can use the Bernoulli equation to convert pressure into velocity or velocity into pressure. So the pressure is given, we can convert this pressure into velocity. Okay, once we get the velocity we can easily calculate the flow rate. Okay, because the area is given for the larger section. Okay, so let's move on. So here we apply. First we assign 2 points, 0.1 and 0.2. This is the larger section, this is the smaller section. Okay, so what is the pressure at 0.1 and what is the pressure at 0.2? So first we apply the Bernoulli equation. Since 0.1 and 0.2 are lying on the same reference plane, so Z1 is equal to Z2 and V2 is equals to 0, because the stagnation pressure at 0.2 is 0, because the pitot tubes give you the technique to measure the stagnation pressure. So at stagnation 0.2 the velocity is 0. Okay, so we insert this value in this equation, and finally we reduce this equation to P1 over gamma, V1 over 2G, P2 over gamma. So now we can calculate P1 and P2 separately, because P1, this is the 0.1, and from here to here this is the height of the column. The height of the column is x. Okay, so P1 is equals to gamma into x, yeah, gamma into h. So we bring this gamma to the other side, so P1 over gamma is equals to x. Now at 0.2 this is the height of the column, so P2 will be equal to x plus 0.2. So this is going to be x plus 0.2. So we insert the value of P1 and P2 in this equation, and this equation is finally reduced to V1 is equals to under root 2G into 0.2. Okay, and finally we got the velocity 1.98 meter per second. Now the velocity is known, we can easily calculate the Q. So by using V1 and A1 we calculate the flow rate. Since the flow rate throughout the pipe is constant, so whatever is the diameter of the smaller pipe or the larger pipe, okay, the flow rate will be remain same for any diameter D. It is D, it's going to be more smaller, D1, D2, whatever. So the flow rate will be same throughout the pipe. So this is the problem we solved. So next, please, this is almost the same problem, but here the flow is going into the divergence section, and we are using a U-tube manometer. inverted U-tube manometer. So let's solve this problem by yourself, and if you have any problem we can discuss. So let's move on to the other problem. Okay, so here you can see here also the problem related to the variable area. Okay, area of the pipe is varying, but here you can see if I take this pipe as a horizontal, okay, this will become the same case that we have discussed before, but now this pipe is making some angle with the horizontal angle. So if the pipe is making some angle theta, so what are the difference we can see in this equation? So let's see what is our objective in this problem. So water flows through a pipe reducer. The pipe is reducer as shown in figure. The static pressure at 1 and 2 are measured by the inverted U-tube manometer containing oil of specific gravity Sg less than 1. Okay, since this is the inverted U-tube manometer and specific gravity of oil is less than 1, if it is greater than 1, what will happen? This fluid cannot be used as a manometric fluid because it will come below the water because it's heavier than the water. So since it is lighter than the water, so the fluid is staying above the water. Okay, that's why the specific gravity is less than 1. So now we have to determine the height h. So we have to determine the height h. So determine the height h, okay, because height h is the function of pressure at point 1 and point 2. Okay, so we can find out the pressure P1 and P2 by using the Bernoulli equation and we convert this velocity into the pressure. Okay, so first we will measure the pressure at point 1 and point 2 by using the Bernoulli equation, and then whatever the value we found by using the Bernoulli equation we will equate with the equation of U-tube manometer, because the P1 and P2, the pressure difference is equal to the height of the column. Okay, and P1 and P2 in the Bernoulli equation is equal to the velocity difference of velocities. Okay, so let's see, and the difference of elevations as well, because it's making some angle theta here. So let's see here. So we are applying now the Bernoulli equation. Okay, so this is the center line or the reference plane. Okay, so this point is z1 minus z2 below the point 2. Okay, so now apply the Bernoulli equation at point 1 and point 2. So this is the Bernoulli equation. Okay, and now we separate the P1 and P2. So because we have to equate this P1 and P2 with the height of the column, so we separate P1 and P2 in this form. So initially what we took the pressure at one side and we took the Z and the velocity to the other side. So we convert the velocity in the form of area, because velocity is not known but the area is known. Okay, this is the area is known, A1 and A2. The diameter is known, this is D and this is the capital D, D1 and D2. So here Q is equals to A1 V1, Q is equals to A2 V2. So we replace this velocity with you take this because we took this V2 we took this from here, the V2 common. So what will happen, it will become V1 over V2. So if you bring the V2 here and take the A1 here, so V1 over V2 will be equal to V2 over, if you bring this V2 here, what will happen? If you bring this V2 here, what will happen? A2 over A1. V1 over V2 will be equal to A2 over A1. So we replace V2 over A1 with A2 over A1. Okay, and finally, okay, so this is the equation number 1. Now we make the another equation for the manometer. Okay, so we consider this is our height of the column. This is we are considering as a reference point, because whatever the pressure is here, same pressure is acting at this point. So at these 2 points the pressure are same. So we start from here. So this is point 1, we start from here. Okay, the pressure at point 1 equal to plus, we are going up. The pressure at point 1 P1, we are going up, the pressure is going to be minus. So from here to this point, okay, from here to this point, at this point it is gamma into Z2 minus Z1. So this is minus gamma Z2 minus Z1. Then we are going further up, so that means gamma into L1. So this is minus gamma into L1. Then we are going further up, that means gamma minus gamma into H. So minus gamma into H. Okay. So now you can bring this equal sign here. Okay, bring this equal sign here. If you bring this equal sign here, what will happen? This will go to the other side and this will go to the other side. Okay, so P2 minus gamma L minus Sg into gamma H. So this is point 2. So this is pressure P2. Then you are going up. So what will happen? This is gamma into L. So gamma into L minus, because going up, so minus, this gamma L will come this side, so gamma minus into L. So again this will come, you are going further up, so the specific gravity of the fluid is changed to Sg into specific weight of the water into height of the column. So this will come also to the other side. So when you take it to the other side, this will become positive, this will become positive, this will become P2. So P1 minus P2 will be equal to this. So now if you compare this and this, so finally you will end up this equation. Okay. So here you have to find out, determine the H, and you can determine the, if you know the flow rate. Okay, if you know the flow rate, if you know the area or velocity, you can easily calculate H from here. But if you know the flow rate and area, or you can easily calculate H by using this equation. So some important points to be noted down here, which is mentioned in the comments. You see, the difference in elevation Z1 minus Z2 was not needed because the change in elevation term in the Bernoulli equation exactly cancel the elevation term in the manometer equation. In both the equation, you see, if the velocity is known or the area is known, you don't need H. You can easily calculate H. If the flow is known and the area is known, you don't need Z. In this case and in this case, in both the cases you don't need Z. You can easily calculate height of the column. Okay, this is the first point. Okay, because the Z in manometer and they are cancelling each other, that's why it is out of the equation. Okay. Second, however, the pressure difference P1 minus P2 depends on the angle theta, because the elevation Z1 and Z2 in equation 1. Okay, thus for the given flow rate, pressure difference P1 and P2 as measured by the pressure gauge would vary with the theta. Okay, so this is also another point. Okay, if you want to find P1 and P2, okay, the P1 and P2 is dependent on Z1 and Z2. If the Z1 and Z2 will vary, that means the P1, the pressure will vary. Why? Because there is a hydrostatic pressure, because you see the hydrostatic pressure at point 2 is less, the hydrostatic pressure at point 2 is more. But if you make this pipe straight, what will happen? The hydrostatic pressure at 1 and 2 will be same. But if you increase the if you make some angle, so what is happening? The pressure at, so to calculate the P1 minus P2, there is a factor of Z2 minus Z1, so it has to be considered. But to calculate the height of the column, we don't see any Z, we don't see any factor of theta. So but the manometer reading H would be independent of theta. So this is an important example that you have to solve it properly. So let's move on to the important topic, which is the use of Bernoulli equation in the form of flow rate measurement. So why do we measure the flow rate? So why it is important? We measure the flow rate to in the quantification of bulk fluid and its movement. So we need to know how much fluid we have transferred from one point to another point. Okay, how much fluid we have stored. Okay, so to measure such to measure the quantity of fluid, okay, we need a flow measuring device. Okay, and also the flow measuring device is important for the sale and purchase of fluid, for regulating a process, for producing the desired pressure difference, need to maintain the flow rate, etc. For the process also, we need to regulate a particular amount of flow, particular amount of fluid, okay, per unit time. So for all these, this is very important to know the flow rate of the fluid. Okay, so to measure the flow, a flow sensor is introduced into the flow. Flow sensor is basically determine the pressure difference or the pressure across the flow measuring device. Okay, so here you can see this is the flow measuring device. Okay, most flow sensor requires a straight section of pipe before and after the sensor, because you see, if the pipe is not straight right after the flow sensor, okay, sensor, what will happen, due to the fluctuation, the pressure you will read or the height of the column what you will read, it will not be appropriate, it will be fake, it will be not real. So if the pipe is smooth, the streamline will be smooth and you will get the right pressure height, and then you will be able to convert that pressure height into the velocity. So here several reasons rely on the pressure drop occurring as a fluid flows through a sensor. Okay, so whenever the fluid flows through the sensor reads the pressure drop. So the relation between flow rate and the pressure difference is determined by the Bernoulli equation, assuming that change in elevation is negligible. Okay, so because you see, the Bernoulli equation basically it's convert the pressure in the form of velocity or velocity in the form of pressure. So flow measuring device are nothing but is the restrictions in a pipe. Okay, so this is a kind of a restriction. This is basically called a orifice. Okay, so this is the restriction of a pipe. How the orifice looks like, if this is a circular pipe, this is a circular disc inside. Okay, and if you make a hole in the disc, what will happen, this you will find this opening and this will work as an orifice. Okay, so to calculate the pressure, okay, to calculate the pressure across the, so apply the Bernoulli equation between the inlet section and the exit section. So this is the Bernoulli equation. Okay, so here consider this is 0.1 and this is 0.2 or 0.3. Okay, so it indicates that the total energy at 0.1 is equal to total energy at 0.3, okay, plus the change in friction losses, where sigma f represents the total friction loss. It is usually assumed negligible. Okay, if we are dealing with the if we are dealing with the ideal fluids, this sigma f is 0, but if we are dealing with the actual fluid, this will not be equal to 0. That means the total energy at 0.1 will not be equal to total energy at 0.2 unless we add these losses, because you see, whenever the fluid enters from the open area to the shorter area, what will happen, because of the smaller area, the friction will increase, the heat will generate. That means the energy will be lost in the form of heat, in the form of noise. Okay, so we cannot ignore that. So but in the ideal condition, we do not consider such losses. Okay, the fluids are ideal. So in that case, the total energy at 0.1 will be equal to total energy at 0.3. Okay, so here we apply the Bernoulli equation. Now let's see what are the equipments normally we use, to what are the type of meters we use to measure the flow rate. So here, during a process, most of the parameters are fixed, and therefore if pressure differences is measured, then the flow rate can be calculated from the Bernoulli equation. Because you see, if you know, because here in the equation you can see if this is 0, so you have two things, pressure difference and the velocity. If you are able to find out the pressure difference, that means you are able to find out the velocity. If you find out the velocity, you can easily calculate the flow rate by using the equation Q is equals to VA. So let's see to the next slide. You see the difference, the pressure difference can be measured either by using the manometer tube, piezometer tube, U-tube, inclined U-tube manometer, okay, Bourdon pressure gauge, or strain gauge pressure transducer. There are so many type of instruments that can use to measure the pressure before and after the obstruction. Okay, so this is a U-tube manometer we used here, and we can use other type of measuring devices also. Okay, so here the low pressure, okay, there is another important point. The low pressure at the point of highest velocity creates the possibility for the liquid to partially vaporize. It might remain partially vaporized after the sensor called flushing, or it might return to the liquid as the pressure increases after the lowest pressure point called cavitation. Here we will discuss later in detail. We want to avoid any vaporization to ensure proper sensor operation and to retain the relationship between the pressure difference and flow. Okay, so vaporization can be prevented by maintaining the inlet pressure sufficiently high and the inlet temperature sufficiently low. So here we can see the three commonly used type of flow meters are illustrated. The three types means three types of different obstructions. Okay, the orifice meter, the nozzle meter, and the venturi meter. The operation of each is based on the same physical principle. As increases in velocity causes a decrease in pressure. Okay, so this is the phenomena. So here the flow meter in pipes using restrictions, the flow meter measurements in pipes using restrictions. So this is the flow meter. This is called the orifice. When we use a circular disc in the circular pipe and making a hole, so this work like an orifice. When we make a reducer within the circular pipe, so it works like a nozzle. Or when we reduce the area in that way, in the little bit smoother way, so it's going to be nozzle. So if we make a pipe section like this, so this is called the nozzle section, this is called throat, and this is called diffuser section. The nozzle section is little sharp, the converging portion is little sharp, and diverging section is little bit smooth. Okay, so this is called orifice, this is called nozzle, okay, and this is called venturi. So what is the difference? In the orifice you can see the fluid entering to the orifice. Okay, after discharging, the fluid layers are separate from each other, because here the velocity is low and the pressure is high, but when it enters to the orifice, the velocity increases. Because of the velocity increases, the pressure reduces. Because of the pressure reduce, what happens? The boiling temperature is reduced. If the boiling temperature is reduced, what happens? There is vaporization. So this vaporization basically affects the cause of the cavitation. So here you can see the cavitation, the space. Okay, so if you have a sensor here, you will not get a right reading. Okay, so but you will get some reading, but the reading will not be accurate or appropriate, okay, or trustable. So if you take the nozzle section, you can see in the orifice, the fluid layers are separated each other. Here the depth is the distance is less, here is very more, here is something else. It's very turbulent and abrupt, okay, in the form of orifice. But in the form of nozzle, it seems little organized, but even then there is some portions are vaporized and cavitation effect. Okay, if you insert any measuring pressure measuring device, you will not get an appropriate reading. but here in the Venturi section you can see the fluid particles are not as separated, they are smooth and aligned. Okay, you don't see any vaporization or cavitation. So if you insert any pressure gauge, here, okay, or U-tube manometer, you will get almost a realistic and accurate measurement of the pressure difference that will help you. So if you know the pressure, because Z1 and Z2 are equal in all the cases, because the datum line are same, point 1 and point 2 are on the same line, so Z1 and Z2 is cancelled. So in that case the flow is this is the case when the flow is horizontal. Okay, in that case an increase in velocity result in decrease in pressure. So here the pressure is high, velocity is low, but the other side the velocity will be increased and the pressure will be low. Okay, so if you want to find out the P1 and P2, okay, so you can calculate the, if you know V1, if you can find V2 from here, you can easily calculate volume flow rate by using this equation. So if you insert the value of V1 and V2 in the form of Q, okay, so the equation will become is equals to like this. So if you know the pressure difference across two area, you can easily find out the flow rate. Okay, so this is the equation. So if we measure the pressure difference between 1 and 2, we have the flow rate. This is the equation. Just put the value Q V1 in this form, Q over A1, V2 is equals to Q over A2, and simplify it, so you will end up with this equation. So what is the difference between all two? The difference between them is a matter of cost, accuracy, and how closely their actual operation obeys the idealized flow assumptions. So the application is depending on the cost and accuracy of the equipment. So which one you want to use, how precise is your measurement, based on that you decide which meter you are going to use. So this is the end of the lecture. So the related problem from this topic we will do in the next lecture, inshallah.